Right now, as you sit somewhere in the United States, maybe in a quiet suburb in Ohio, a high-rise in New York, a ranch in Texas, or along the Pacific coast of California, two machines built during the Cold War are still moving away from you at over 35,000 miles per hour. They were launched when Jimmy Carter was president, when disco was on the radio, when the personal computer didn't exist in your home. And today, nearly 50 years later, those two spacecraft are farther from Earth than anything humanity has ever created. They are no longer just in deep space. They are beyond the reach of the sun itself, out there past Pluto, past the Kuiper Belt, past the solar wind, at a distance so extreme that radio signals take more than 20 hours just to reach them. Voyager 1 and Voyager 2 crossed a boundary no human-made object had ever crossed before. A boundary we thought we understood. A boundary we were wrong about. When they reached the edge of the sun's influence, the Heliopause, scientists expected one thing. They measured something else entirely. The boundary wasn't where predictions said it would be. The magnetic field didn't behave the way models insisted it should. The density of space itself changed in ways that stunned researchers, and shockwaves from solar storms were still crashing into the probes billions of miles beyond where the sun was supposed to matter. What Voyager detected at the edge of our solar system forced NASA scientists to rethink the shape of the heliosphere, the behavior of interstellar plasma, and even how future spacecraft might survive the journey beyond our star. Tonight we're going to travel with them, slowly, quietly, out past the planets, out past the final whisper of the solar wind, to the place where our sun stops and the galaxy begins. If this kind of real, measured, awe-inspiring science matters to you, take a second to like the video and subscribe. It helps more people discover calm, thoughtful space documentaries like this one. And I'd love to know, what part of the country are you watching from tonight? Leave a comment and tell me your state. It's always amazing to see how far these journeys reach. In 1977, the United States launched two spacecraft within weeks of each other from Cape Canaveral, Florida. They were not designed to leave the solar system. They were not built to survive half a century. They were certainly not expected to become humanity's first interstellar ambassadors. Voyager 2 lifted off on August 20, 1977, followed by Voyager 1 on September 5. Despite its name, Voyager 1 launched second but took a faster trajectory, allowing it to overtake its twin and head outward more quickly. The mission plan was ambitious but finite: conduct flybies of Jupiter and Saturn, gather unprecedented close-up data, and perhaps continue to Uranus and Neptune if funding and trajectory allowed. The spacecraft were built during an extraordinary alignment of the outer planets, a rare configuration that occurs roughly once every 176 years, allowing a gravity-assist trajectory known as the Grand Tour. By carefully passing near one planet, the spacecraft could steal a small amount of its orbital energy, slingshotting outward toward the next target without expending large amounts of fuel. This elegant use of celestial mechanics meant that Voyager 2 would eventually visit Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft ever to explore the latter two up close. Voyager 1, on a slightly different path, would visit Jupiter and Saturn before being directed upward out of the plane of the solar system toward interstellar space. At launch, each spacecraft weighed about 25 kilograms and carried a 3.7-meter-high gain antenna dish to communicate with Earth using NASA's Deep Space Network. They were powered not by solar panels, which would have been useless so far from the sun, but by radioisotope thermoelectric generators fueled by plutonium-238. These generators convert heat from radioactive decay into electricity, providing a steady, long-lasting power source that has kept the spacecraft alive far beyond their intended mission duration. The instruments on board were cutting-edge for the 1970s. Magnetometers to measure magnetic fields, plasma detectors to study charged particles, cosmic ray detectors, photopolarimeters, ultraviolet spectrometers, and imaging systems that delivered some of the most iconic photographs in human history, including the detailed cloud bands of Jupiter and the haunting pale blue dot, image of Earth taken by Voyager 1 in 1990 from nearly 4 billion miles away. But beyond their planetary encounters, the Voyagers were heading toward something far less visible and far more mysterious: the boundary of the heliosphere. The heliosphere is a vast bubble carved into interstellar space by the solar wind, a continuous stream of charged particles flowing outward from the sun at speeds of about 400 to 800 kilometers per second. This wind carries the sun's magnetic field with it, creating a protective cocoon that shields the planets from a significant fraction of galactic cosmic radiation. As the solar wind expands outward, it eventually slows down when it begins to encounter the interstellar medium, the thin mixture of gas, plasma, and dust that exists between stars. This slowdown creates a termination shock, where the solar wind abruptly decelerates from supersonic to subsonic speeds. Beyond that lies the Heliosphere, a turbulent region where solar and interstellar forces interact. And at the outermost boundary is the Heliopause, the point where the outward pressure of the solar wind balances with the inward pressure of interstellar space. For decades, scientists constructed theoretical models of this structure. They estimated that the Heliopause might lie somewhere between 80 and 100 astronomical units from the Sun, though uncertainty remained because no spacecraft had ever reached that distance. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 93 million miles. By the early 2000s, Voyager 1 had traveled beyond 90 AU, then 100 AU, moving steadily outward at roughly 17 kilometers per second. Signals from the spacecraft took more than 16 hours to reach Earth. Every command sent back required patience. Engineers had to think days ahead, anticipating problems that might arise long after a signal left our planet. In 2004, Voyager 1 crossed the termination shock at about 94 AU, confirming the first major boundary of the Heliosphere. The solar wind slowed dramatically, and particle detectors registered changes consistent with entering the Heliosphere. This was already a milestone. Humanity had reached a region previously accessible only to theoretical physics. Yet the true goal remained ahead. As Voyager 1 moved deeper into the Heliosphere, scientists watched for signs of the Heliopause. They expected a dramatic change in magnetic field direction, since the Sun's magnetic field lines are oriented differently from those of the galaxy. They expected a drop in solar particles and a rise in galactic cosmic rays. They expected a clear transition, but space is rarely so tidy. By 2012, Voyager 1 was about 121 AU from the Sun. Its plasma instrument unfortunately had failed years earlier, limiting direct measurement of solar wind speed. Researchers had to rely on indirect clues from cosmic ray detectors and magnetometers. In August 2012, Voyager 1 detected a sudden, sustained increase in high-energy galactic cosmic rays, accompanied by a sharp drop in lower-energy particles originating from the Sun. It appeared to have crossed into interstellar space. Yet the magnetic field direction did not change as dramatically as predicted. This puzzled scientists. Had the spacecraft truly left the Heliosphere, or was it in some transitional boundary layer? Months of analysis followed. Then in 2013, researchers confirmed that Voyager 1 had indeed entered interstellar space. The key evidence came from plasma wave measurements triggered by a solar storm that had erupted from the Sun in 2012. The shockwave from that eruption traveled outward for more than a year before reaching Voyager 1. When it did, it caused the surrounding plasma to oscillate. By analyzing the frequency of those oscillations, scientists could calculate the density of the plasma around the spacecraft. The measured density matched expectations for interstellar space, not the Heliosphere. It was a remarkable detective story. A solar storm launched billions of miles away provided the final proof that humanity's farthest probe had crossed the boundary between our star's domain and the galaxy beyond. Voyager 2 followed a different trajectory, remaining within the plane of the solar system. It crossed the termination shock in 2007 at about 84 AU, a significantly closer distance than Voyager 1's crossing. This asymmetry suggested that the Heliosphere was not a perfect sphere, but was shaped by external forces, likely the pressure and magnetic field of the interstellar medium. In November 2018, Voyager 2 crossed the Heliopause at about 119 AU. Unlike its twin, Voyager 2 still had a functioning plasma instrument, allowing direct measurement of solar wind speed dropping to near zero and interstellar plasma density rising sharply. The boundary was thinner than expected, only a few billion miles thick, and more dynamic. The Heliopause was not a smooth shell but a fluctuating interface shaped by magnetic interactions and pressure variations. These crossings marked a turning point in space exploration. For the first time, instruments built by human hands were sampling material that originated beyond our solar system. The interstellar medium detected by Voyager was denser than some models predicted, suggesting that our local galactic environment is not uniform. The magnetic field beyond the Heliopause was surprisingly aligned with the solar magnetic field, challenging assumptions about how sharply the boundary would bend field lines. Perhaps most astonishing was the persistence of solar influence. Shockwaves from solar eruptions continued to propagate through the heliosheath and into interstellar space, indicating that the Sun's reach extends farther and more dynamically than once thought. As Voyager moved outward, it revealed that the boundary of our solar system is not a hard edge, but a living frontier shaped by plasma physics on scales of billions of miles. The heliosphere itself may resemble a comet-like structure with a rounded nose facing the direction of the Sun's motion through the galaxy, and a trailing tail extending far behind. Recent models even suggest a more complex, bubble-like or croissant-shaped structure influenced by the Sun's magnetic field. Each data packet from Voyager forces refinements to these models. Meanwhile, back on Earth, engineers carefully manage dwindling power supplies. Each year, the radioactive decay in the generators reduces available electricity. Instruments are turned off one by one to conserve energy. Yet even with minimal systems active, the Voyagers continue to transmit invaluable data across nearly 15 billion miles in the case of Voyager 1. The signals are faint, far weaker than a cell phone transmission, but enormous radio antennas across California, Spain, and Australia listen patiently, amplifying whispers from the edge of interstellar space. The fact that spacecraft designed with 1970s computing power, less than a modern digital watch, are still functioning in 2025 is a testament to robust engineering and careful stewardship. But more than that, it is a testament to patience. The journey to the edge of the solar system is not measured in days or months. It is measured in decades. Voyager's discoveries at the Heliopause were not sudden surprises delivered overnight. They were the result of 40 years of steady outward motion, of signals crossing billions of miles, of scientists waiting and reanalyzing and questioning their assumptions. What Voyager detected at the edge was not just new data. It was proof that the boundary of our solar system is more complex, more dynamic, and more surprising than theory alone could predict. And in that realization lies something profoundly human even at the very limits of our reach. The universe still has the power to surprise us. When scientists first began modeling the outer boundary of the solar system in the late 20th century, the heliopause seemed, at least on paper, like a relatively straightforward concept. The Sun emits a continuous outflow of charged particles known as the solar wind. That wind expands outward in all directions, carrying the Sun's magnetic field with it, inflating a vast bubble in space. Eventually, that outward pressure must meet resistance. Beyond our solar system lies the interstellar medium, an environment composed of sparse plasma, neutral hydrogen atoms, trace heavier elements, magnetic fields, and high-energy cosmic rays drifting between stars in the Milky Way galaxy. Where the outward push of the solar wind balances the inward pressure of that interstellar medium, a boundary forms. That theoretical dividing line was named the Heliopause. For decades, astrophysicists estimated its distance using computer simulations, indirect measurements, and the physics of plasma dynamics. Most predictions placed it somewhere around 100 astronomical units from the Sun, perhaps slightly farther depending on solar activity. It was expected to behave like a smooth, comet-shaped shell, bulging in the direction the Sun travels through the galaxy and trailing into a long heliotail behind it. It was expected to be dramatic, a clean transition, a sharp magnetic shift, a definitive crossing. But when Voyager 1 actually approached that boundary, space did not behave the way the equations had promised. By 2010, Voyager 1 was more than 115 astronomical units from the Sun, moving through a region known as the heliosheath, the turbulent outer layer of the heliosphere beyond the termination shock. The solar wind there had already slowed from supersonic to subsonic speeds. Instead of a steady outward stream, it churned and swirled, compressed by pressure from interstellar space. Instruments on board Voyager 1 began detecting changes that hinted something unusual was happening. The cosmic ray subsystem recorded rising levels of high-energy galactic cosmic rays, particles originating from distant supernova explosions and other violent astrophysical events across the Milky Way. At the same time, lower energy particles associated with the Sun began to drop sharply. It was as though the protective bubble of the heliosphere was thinning, allowing more galactic radiation to seep inward. Then, in August 2012, something dramatic occurred. Within a matter of days, Voyager 1 recorded a sudden and sustained spike in galactic cosmic rays, while solar particles plunged to a fraction of their previous levels. It was one of the most abrupt transitions in particle intensity ever measured. Many scientists immediately suspected that Voyager 1 had crossed the heliopause and entered interstellar space. But there was a problem. The magnetometer readings did not show the expected sharp change in magnetic field direction. According to prevailing theory, the Sun's magnetic field lines, carried outward by the solar wind, should have a distinct orientation compared to the magnetic field embedded in interstellar space. Crossing the Heliopause should have produced a noticeable rotation in the field direction. Instead, Voyager 1 detected a magnetic field beyond the boundary that was surprisingly aligned with the solar magnetic field inside it. This contradiction sparked months of debate within the scientific community. Had Voyager 1 truly left the heliosphere, or was it inside a transitional, magnetic highway region, a kind of porous boundary layer where interstellar particles could enter but solar magnetic fields still dominated? Some researchers proposed that the heliopause might not be a smooth shell at all, but a layered, rippling interface shaped by magnetic reconnection, a process where magnetic field lines from different domains break and reconnect, allowing energy and particles to pass through. Others suggested that the boundary might be folded or distorted by external pressure from the interstellar medium, creating regions where the magnetic fields happen to align more closely than predicted. The definitive evidence came from an unexpected source, a solar storm that had erupted from the Sun in March 2012, months before the particle spike. That eruption launched a powerful coronal mass ejection, a billion-ton cloud of magnetized plasma, hurtling outward through the solar system. It traveled far beyond the orbit of Neptune, far beyond Pluto, racing through the Heliosphere. More than a year later, in April 2013, the shockwave from that eruption reached Voyager 1. When it passed the spacecraft, it caused the surrounding plasma to oscillate like a plucked string. Although Voyager 1's primary plasma instrument was no longer functional, its plasma wave subsystem could detect these oscillations. By measuring their frequency, scientists calculated the density of the plasma around the spacecraft. The result was clear. The density matched the expected value of interstellar plasma, roughly 40 times higher than that inside the heliosphere at similar distances. It was an extraordinary moment. A solar eruption had effectively illuminated the darkness around Voyager 1, revealing the nature of the space it now occupied. The data confirmed that Voyager 1 had indeed crossed the heliopause in August 2012 at a distance of about 121.6 astronomical units from the Sun, roughly 11 billion miles from Earth at the time. The boundary was not where many models predicted. It was farther out than some estimates and thinner than expected. More importantly, its magnetic behavior did not match theoretical expectations. Voyager 2's crossing in November 2018 added even more complexity to the story. Traveling along a different trajectory and still equipped with a functioning plasma instrument, Voyager 2 provided direct measurements of solar wind velocity dropping to nearly zero as it passed through the heliopause at approximately 119 astronomical units. Unlike Voyager 1, Voyager 2 observed a clearer change in magnetic field direction, yet the transition still occurred across a surprisingly narrow region, only about 1 billion miles thick. In cosmic terms, that is razor thin. These two crossings, separated by billions of miles and 6 years of time, revealed that the heliopause is not a uniform shell but a dynamic, asymmetrical boundary shaped by local conditions. One of the most surprising discoveries was the continued influence of the Sun far beyond the heliopause. Scientists had assumed that once outside the heliosphere, solar activity would have minimal impact. Instead, Voyager 1 and Voyager 2 both detected shockwaves from solar storms propagating through interstellar space, compressing plasma and altering magnetic fields billions of miles beyond where the Sun's influence was thought to end. It was as though the Sun's breath extended farther than anyone realized, its eruptions echoing into the galaxy. These findings forced researchers to reconsider the size and structure of the heliosphere. Rather than a static bubble, it appears to expand and contract with the 11-year solar cycle, breathing outward during periods of high solar activity and relaxing inward during quieter times. Even more puzzling was the structure of the magnetic field beyond the heliopause. Instead of sharply diverging from the solar magnetic orientation, the interstellar magnetic field seemed to drape itself around the heliosphere, bending in response to the Sun's motion through the galaxy. This draping effect may explain why the magnetic direction did not rotate as dramatically as predicted at Voyager 1's crossing. It suggests that our solar system is not simply flowing through a uniform galactic environment, but interacting with it in a complex magnetic dance. The Sun moves through the Milky Way at about 40-48,000 miles per hour, orbiting the galactic center once every 225 to 250 million years. As it travels, It encounters varying densities and magnetic conditions in the interstellar medium. The heliosphere is therefore shaped not only by the Sun's internal dynamics, but also by the properties of the region of the galaxy we happen to inhabit. Data from the Voyagers indicate that our local interstellar medium is denser and more magnetically structured than some earlier estimates suggested. This has implications for understanding cosmic ray shielding, space radiation hazards, and the broader galactic environment. Galactic cosmic rays are high-energy particles that pose risk to spacecraft electronics and human explorers beyond Earth's protective magnetosphere. The heliosphere acts as a partial shield, deflecting many of these particles, but the strength and shape of that shield depend on the structure of the heliopause and the interstellar magnetic field. By directly sampling the region beyond, Voyager has provided the first ground truth measurements of how effective our solar bubble truly is. Another unexpected observation was the relative smoothness of the plasma density increase beyond the heliopause. Rather than an abrupt wall, the transition appeared to involve subtle fluctuations, with plasma densities rising in waves and magnetic fields pulsing in response to distant solar activity. This suggests that the heliopause may be permeable in places, allowing some mixing between solar and interstellar particles. Magnetic reconnection events at the boundary could create temporary channels through which particles travel in both directions. In effect, the heliopause may resemble a coastline rather than a brick wall, shaped by tides, currents, and storms. The shape of the heliosphere itself has become a subject of renewed debate. Earlier models envisioned a long comet-like tail stretching tens of billions of miles behind the Sun. More recent simulations, informed by Voyager data and energetic neutral atom maps from NASA's Interstellar Boundary Explorer, suggest a more complex structure, possibly resembling a croissant with two lobes shaped by the Sun's magnetic field. If this is correct, the heliosphere's tail may be split into twin jets rather than a single elongated wake. Voyager's measurements of particle distributions and magnetic orientation continue to refine these models. What makes these discoveries especially remarkable is the technological context. The Voyagers carry less computing power than a modern smartphone. Their memory is measured in kilobytes. Commands are sent in binary sequences across nearly 15 billion miles. Yet their instruments, carefully calibrated and maintained, continue to deliver data that reshapes astrophysical theory. Each bit of information arrives faint and delayed, taking more than 20 hours to travel one way at the speed of light. Communication requires extraordinary precision from NASA's Deep Space Network, whose 70-meter antennas track the spacecraft against the cosmic background with astonishing accuracy. The boundary that was supposed to be predictable turned out to be layered, dynamic, and surprising. It was farther than expected in one direction, closer in another. It was thinner, more magnetically complex, and more permeable than theory suggested. It allowed solar shockwaves to travel through it. It aligned magnetic fields in ways that defied simple models. In short, the heliopause was not the clean dividing line scientists imagined. It was a frontier, alive with plasma turbulence and magnetic tension. For humanity, this matters deeply. Any future attempt at interstellar travel will have to pass through this boundary. Understanding its structure is essential for predicting radiation exposure, navigation conditions, and spacecraft durability. Voyager's journey has transformed the heliopause from an abstract theoretical surface into a mapped, measured region of space. It has shown us that the edge of our solar system is not a fixed border but an ever-changing interface between our star and the galaxy beyond. And perhaps most profoundly, it reminds us that even at the very limits of our reach, the universe refuses to be simple. The boundary was not where we thought. It did not behave as expected. And in that deviation from prediction lies the true beauty of exploration.